In this example, we're told we have a 1/16th scale model of a weir. A weir is just basically an obstruction in the flow of free surface flow. So we have kind of like a river headed from left to right here. And the river has a height that's taller than the weir, so there's flow over that weir, and then it goes to a smaller height. So that's the weir is kind of like an incomplete dam. You still have flow going over the top of it. But we're told that we have a 1/16th scale model of a weir, and there's a measured flow rate Q. Q is just the volumetric flow rate of the water going over the weir. We're given that that's 2.1 cubic feet per second. When the upstream water height is H equals 6.3 inches, so that's just the height above the weir far upstream. We know that the flow rate is known to be a function of the acceleration due to gravity, G, the weir width into the page, B, so that's the distance in and out of the page, and the upstream water height, H. Furthermore, the flow rate is found to be directly proportional to the weir width, B, so that's another piece of information we know. And we're asked, what is the flow rate over the prototype weir when the upstream water height is 3.2 feet? So let's, when we look at this, we'll realize this is a scaling problem, right? So we have some model, and then we have a prototype with different dimensions. We want to see how the scale, so this will be a dimensional analysis kind of problem. So the first thing we'll do is write down how the flow rate depends on the other variables. So we're told that the flow rate is a function of the acceleration due to gravity, G, the weir width into the page, B, and the upstream water height, H. Okay, so we're given that, and then we'll do our standard dimensional analysis approach. We'll write down the basic dimensions associated with each of those variables. So the volumetric flow rate will be length cubed per time. For acceleration due to gravity, that's length over time squared. B is the distance in and out of the page, so that's a length, and H is, of course, a length. So we only have two basic dimensions here, a length and a time. Let's go ahead and find out the number of pi terms that we'll have. Number of pi terms is the number of variables minus the number of reference dimensions. Number of variables is 1, 2, 3, 4. And the number of reference dimensions is 2, and those are length and time. We need both of those. So we're going to get 2 pi terms, ultimately. So to find those pi terms, we'll use the method of repeating variables. So we need to choose some repeating variables to make the other variables dimensionless. So the 2 repeating variables I'll choose, they need to be from the right-hand side. I'm going to just choose G and H as my repeating variables. G has a time in it, H has a length in it. And then we'll go ahead and find our pi terms from those. So the first pi term will involve Q. So I'll multiply it by each repeating variable raised to a power. I'll write down those variables in terms of their dimensions. So pi 1 will just be length to the 0, t to the 0. When you raise something to the 0 power, it's just equal to 1. So the left-hand side is dimensionless. The volumetric flow rate we said was L cubed over time. G was L over t squared raised to the A, and then H is just L raised to the B. Let's go ahead and look at each dimension separately. So the length will have 0 on the left-hand side. That's this 0. On the right-hand side, we have 3 plus A plus B. We'll do the same thing for the time. Left-hand side it's 0. On the right-hand side it's a minus 1 minus 2A. So you can see the minus 1 comes from here. It's in the denominator. And here we have a minus 2 times A. So that gives us the minus 2A. So from these, you'll find that A is equal to a minus 1/2. And then we'll have, we can combine that. Let me change that. We can use that A minus equal to minus 1/2 up here. So this will be 3 minus 1/2. So that'll be what, 5/2. So B will equal minus 5/2. I've done that correctly. So then our first pi term will be Q times G to the minus 1/2 times H to the minus 5/2, or we'll just write it a little more compactly as Q over square root of G, H to the 5th, the whole thing square rooted. So that's our first pi term. Our second pi term involves b, because g and h are repeating variables, so the only non-repeating variable is b. And you can see very quickly that since b has dimensions of length, all we have to do to make that dimensionless is divide through by h, one of our repeating variables here. So pi 2 will just be b over h, and we found that one just by inspection. We can just see very quickly that that is a dimensionless term. And that's it. That's all those are our only two pi terms, right? From our Buckingham pi theorem, we only had two pi terms, so we just found both of them. Now let's just verify that those are indeed dimensionless. Pi 2 is pretty obvious. It's just a length over length, so that one's okay. Pi 1 will be a length cubed over time for the q, dividing through by square root of gravity, so that'll be t over L to the 1/2, and dividing through by h to the 5/2, so that'll be 1 over length to the 5/2. So the t's cancel out. In the denominator, L to the 1/2 times L to the 5/2 will be L to the 6/2, which is L cubed, and that cancels out with that L cubed. So this one's okay as well. It's good to just double check. So what we get in the end is, in terms of dimensionless quantities, our relationship is the dimensionless flow rate, oops, that's up to the 5th, is a function of b over h. So that's what our expression looks like in dimensionless terms. So we can rewrite our original dimensional equation here, and it'll look like this. We still don't know what that function is right now. We just know it's some function. Dimensional analysis doesn't necessarily tell you what that function is. We just know that we can rewrite the original equation like in this form. That's all that dimensional analysis will tell you. Now we're also given one other piece of information in this problem statement. If you come back up here, you'll see that it says the flow rate is found to be directly proportional to the weir width b. Okay, so what that means is that the flow rate is proportional to b, right? So if I double b, then I double q. Well, that tells us now what that functional relationship should be. So this would come from some experimental study, for example, and that one piece of information tells us what that function should be. In order for q to be proportional to b, that function is just it's just going to have to be a constant times b. So it'll look something like this. If I combine these two together, it means that q all over the square root of g h to the 5th, square root the whole thing, has to be some constant times b over h. So now q is in fact proportional to b. I don't know what that constant is without running an experiment and getting some values, but certainly now q is proportional to b. Okay? Well, so now we can actually use it to do some scaling. Let's go back up to the problem statement. And we're asked to find what is the flow rate over the prototype weir when the upstream water height is 3.2 feet. We do know the flow rate when h is 6.3 inches and we have a 1/16 square scale model. So we can go ahead and make use of this information. So let me rearrange this equation just a little bit. Let me just keep the constant on the right-hand side, but bring the b and the h over. So this will be q all over b times the square root of g, and then we'll have, should be, I think it's h cubed, and then the square root of that whole thing. Yeah, that whole thing will just be the constant. So I can, that'll be the same constant whether or not I'm dealing with the prototype or the model, right? It'll be the same constant. So whether I'm dealing with the prototype or the model, it'll still be the same constant. So I can use this, that's the model. So I can go ahead and use this expression to do some scaling here. So I want to find the volumetric flow rate in my prototype. That'll be the volumetric flow rate in the model. And then I'll have b of the prototype times the square root of g prototype h prototype cubed, square root of that whole thing, And then in the denominator, it'll be b of the model, square root of g in the model, h of the model cubed, square root that whole thing. And then, of course, gravity is going to be the same in both. So we can simplify that. Oops, let me just rewrite this whole expression and make it look a little cleaner. Okay, so we're down to this point, and we're told that the volumetric flow rate in the model is 2.1 cubic feet per second. We're told the H in the model was 6.3 inches. And let me just convert that over to feet since the volumetric flow rate is in feet. That comes out to be 0.525 feet. We know that we have a 1/16 scale model. That means just the geometry of the weir is scaled in that manner. So the depth into the page for the model is 1/16 the depth into the page for the prototype. And then the H of the prototype, we're told in the problem statement, is 3.2 feet. That's in our model, it's only 6.3 inches, and we measured that volumetric flow rate. The prototype, we're told that it's 3.2 feet. This is a much bigger scale. We want to know the volumetric flow rate for that condition. So we can go ahead and plug these values, plug them all back in up into here, and when you do that, you'll get the volumetric flow rate for the prototype is 506 cubic feet per second. So obviously a much larger value than what we had for our model. Okay, so let me just kind of recap what we've done here. We did our standard dimensional analysis approach. We read through the problem. We know that we have some sort of model and a prototype, so we know it's going to be a dimensional analysis. We're going to have to do some scaling because we're told what the volumetric flow rate is for a 1/16 scale model. We want to know what the volumetric flow rate is for the prototype, the large scale, when the water height here is 3.2 feet. So we did our dimensional analysis, starting with step 1, writing out the volumetric flow rates as a function of these other variables. We went through our standard dimensional analysis, and we came down to this point where we have the boxed in expression. So dimensionless flow rate is a function of the dimensionless depth into the page. But we were given one other piece of information, and that is just based on some experimental studies or some other analysis, the volumetric flow rate is proportional to the depth in and out of the page. So that told us what that functional relationship looked like. It has to look like this in order for Q to be proportional to B. It's just going to be dimensionless flow rate is equal to a constant times the dimensionless depth into the page. And that constant will be the same whether it's the model or the prototype. So that's how we got to that point. Then we just rearranged the equation to get to this point. We had numbers given in the problem statement from our model, knowing that also that we have a 1/16 scale model, and then some information from our prototype. We plugged that all in, and we could find the volumetric flow rate in the prototype. So this is where dimensional analysis really shows its power, is we can rewrite our more complex dimensional equation in a dimensionless form. It simplifies it a bit, and with a little bit of experimental data, you can, in many cases, determine how you can scale quantities from very different sizes. It's a pretty useful technique. Okay, we'll go ahead and end the example there.